gambit, not only is it trying to introduce what we're going to talk about, but it's going to sort of set the very base. So it's got a lot of math, measurements, and talking about what is known as matter. So matter, see how many people actually remember some definitions. So definition just for chemistry, biology, these are all systematic studies. Let's see if I can change my color. Never like that. They're systematic studies of some topic. And the changes it undergoes. That's this, sorry. That's what the definition for chemistry is. But then it gives you this word matter. And there was two criteria that matter had to have. There's two characteristics that make something matter. It's anything that has mass and takes up space. Okay, so those are considered the primary characteristics. It has to have some substance. It has to have mass. And on Earth, you're talking about weight. You're thinking about it. And it takes up space. So the three different forms of matter I've got listed: solids, liquids, and gases. So matter can be a solid, it can be a liquid, it can be a gas. It may change forms. So if you're looking at particles of a certain type of matter, solids versus liquids versus gases, which ones do the particles, are they the furthest apart? Gases. So if we were to just use these little blobs as particles, gases, the particles are very far apart. In fact, they really rarely touch. So that's like the air in this room. 79% is nitrogen, about 21% is oxygen. There's water vapor, carbon dioxide. There's much smaller concentrations of minor gases. But these molecules are floating along. But they're so far apart, the odds of them actually coming into each other, bouncing off each other, slim to none. So in order for something to become a liquid, what has to happen to those particles? Yeah, they have to come together. They have to get closer. In fact, they do come in contact with each other. However, compared to solids, there is a little bit of space between them, and this allows them to move. So they are not rigid, stuck in their area. They have this ability to flow. But the particles are much closer together. Whereas solids, are when you have particles of matter in a regular, ordered arrangement, much more rigid. So they describe solids, liquids, and gases as whether or not they have a defined or an indefinite shape and volume. So what would you say with solids? Defined or variable? If you look at the table. It's defined. So the shape, if you have a solid and you put it down, it stays there. Okay, it doesn't move around. So it has a very defined shape, and it takes up the same amount of space. So it's going to have a defined volume. Which one of these changes when it becomes a liquid? So if you have a cup of water in a cup, or a cup of water that you spill on the floor, is it still a cup of water? No. So do you lose water? Does it just disappear? It just changes its shape. So still 8 ounces of water, it's now just spilled all over the floor. Okay, so it's spread out in a real thin layer. But if you could gather it all back up, you would have that 1 cup. So that's the same volume. So liquids, they have a definite volume. So that is going to enclose them. They're going to have this certain amount of space they take up. But they have an indefinite shape. They take the shape of whatever their container is. They have that ability to flow. So then what happens when you're talking about a gas? So the air in this room, right, has an indefinite shape and volume. They expand to fill whatever the container is. And if you've ever like had an oxygen tank, if you've like taken care of patients, had the compressed air, that they have taken that and compressed it into a smaller volume. So gases can be compressed, whereas liquids and solids cannot. And when it gets released, it just expands to fill whatever that space is. So indefinite shape and volume. So if you were looking at these little particles, which particles do you think are moving the fastest? Solids, liquids, or gases? Gases, okay? Because they got all this room. So they're going to be floating and bouncing off of things. So they have the highest activity. We're going to call that kinetic energy. Solids, on the other hand, they just stay there. Okay, so they stay there, they maintain that shape, defined volume. These are going to have the lowest kinetic energy, the lowest activity. So that brings us to another definition, energy. So I always think of matter as being a noun. It's a solid, it's a liquid, it's a gas. So it's like a thing, so it's much more tangible. But energy is not matter. But what are some examples of energy? Like gasoline, electricity. Any others? In what way? Like its movement? Okay, so like water flowing. Even the wind blowing. Like think of all like how energy gets generated. All of the, we have the big huge windmills, the turbines that they collect wind energy. That's mechanical. That's energy of movement. What's another way that we generate energy for human existence? The sun. And that's really like picking up. There's a couple of really big solar farms now that are being used to collect sunlight, solar energy. Did anybody watch Chernobyl? Yeah. The nuclear. All I can tell you is the entire time I was watching that, I think I was like, horrified. People I was watching with, I'm like, this is terrible. This is going to get worse. That's all I kept saying. Just because of the chemistry that I know about it. This is just going to get worse. So all of these are examples of energy. And so it's not the gasoline itself, it's the burning of the gasoline. Okay? It's not electricity itself, it's when you flip the light switch on and off. So like these, they're not actually doing anything because the electricity is not on, but the lights that are on are providing that active energy movement. So you're just sitting, so that's sort of potential or energy not doing movement, but walking, muscle contraction, all example of movement type of energy. These, by energy, we're talking about, instead of a thing, it's really kind of like a verb. So it's like an action. So it's like moving something or causing heat transfer or causing electrons to flow along a wire. So the definition of energy is it's the ability to do what? Does anybody remember this one? It's the ability to do work. So we'll talk about matter, we'll talk about solids, liquids, and gases. But we're also going to talk about energy. We're going to talk about how matter changes forms in chemical reactions and how energy comes into play. So if we were to split matter, we could say we have solids, liquids, and gases. But we can also categorize or classify matter on whether or not it's made of the same particles or if it is multiple types of particles that are physically combined. And so the first big broad sort of classification that they give are mixtures and pure substances. So by definition, when you have a mixture of something, you've just put things together and you stirred it up. Okay, so like cake batter. Okay, so you take cake mix and you take eggs, and the cake mix is sugar and flour and some baking soda in it, some vanilla, and then you got to add the eggs and you got to add oil and water. So you just put all those things together and you blend it up. So a mixture, these things are physically combined. There's more than one substance that's present, right? You know because you put those things in. Before you stir the cake, before you mix the cake, you have all the stuff in the bowl, you can still see, you can see that there's the oil part and the water part. You can see eggs floating in it. You can see the white or the solid powder of the cake mix. That is described as being heterogeneous because you can see parts, you can see pieces, you can see layers. So before mixing, we've got egg, we've got the mix, we've got water, we've got oil. That's heterogeneous. And in theory, you could take and separate it all back out again. I don't know if you've ever done that, accidentally, I put an extra egg in, we'll just pull that one out. There, that's good. Let's just mix the rest of it up and call it. That's heterogeneous. And the way to remember that, so hetero means parts or opposites, so that you can see parts, you can see layers. But after you mix it, then how's it look? So you mix it, you beat it, and you see the eggs all get mixed in, the oil and the water. Do they separate back out? No, when you're done, it's all uniform looking. So after you mix it, it is homogeneous. So homo means the same, so it looks the same. Hetero means different. So you can kind of just think about what the terminology means to help remember which one's which. So homogeneous, it's uniform, doesn't separate out after the mixing. So of all of these, heterogeneous mixtures are the easiest ones to go, that's a heterogeneous mixture, because they look different. Okay, like a bowl of M&Ms, you can see different colors, you can see different parts. So you can tell there's discrete pieces in it. If you have Italian dressing and it separates out. So you can see little spice bits floating about. So you can say, definitely a heterogeneous mixture. Homogeneous mixtures, though, you look at it and you might be I don't know what it is. It's all uniform looking. I don't see any parts. So in that, understanding what the substance is can sometimes help you to figure it out. And I would always give you enough information to be able to figure it out. Pure substances, on the other hand, they're all made of the same particles. So even if you took a pure substance and you split it in half and split it in half, you couldn't separate it back out. So they have the same particles. You can't separate these physically. Couldn't filter it, you couldn't freeze it. If they sit, doesn't matter, it's not going to separate into layers or be able to be partitioned. Sorry, that says same. So here's some examples with these. Pure substances being made of these discrete units, either all the units are exactly the same, so the very smallest particles are exactly the same. Those are what they call elements. Okay, so elements are really the smallest particles of matter. The smallest, you can't make them any simpler, and they actually discovered elements and ended up developing the periodic table. So the periodic table is actually a sort of shorthand version of all of the known elements that are present. So the one that they showed is copper. So if you have pure copper wire, all of the particles that make up that wire are made of the exact same pieces. But now, compounds, this is where things get a little bit murky for some in trying to envision or think about what a pure substance versus like a homogeneous mixture. Compounds are where the particles are the same, but they may be made of more than one element. So these are composed of two or more elements. And the way that you're going to be able to tell that something is a compound is from knowing something about its name. So water, which is H2O. If you look on the periodic table, you have H, which is over in the upper left-hand corner. That's hydrogen. And then you have O, which is the number 8 going all the way across the third from the right column. That's oxygen. And so that is called a chemical formula. So it actually tells you the elements that are contained within each unit of the water molecule. Whereas with copper, and if you look to see where copper is, it's actually number 29. So it's in that little drop down group, and you've got your periodic table if it's a little far away for you to look at. But copper is Cu on the periodic table. And so if you have copper wire, it's nothing but all the same little particles or pieces. Water, on the other hand, is made of two or more substances, and they're combined. So if you take water, you can theoretically separate water into individual particles, and each particle would have 2 hydrogens and 1 oxygen. You could not physically separate those hydrogens and oxygens. They are chemically combined. But water might look homogeneous, right? So like I went and got some water, and so when you look at it, you're like, and this is the challenge that people come in, is that they think of something, and then they're like, well, it's homogeneous looking, so we'll just call it a homogeneous mixture and move on, okay? But copper wire is homogeneous looking. So with that, you actually have to think about what it's made of, okay? Think about the components that make up the part. So for example, like with Gatorade. So what do you know is in Gatorade? What's like their claim to fame? It's got electrolytes. And what are electrolytes? What? They are salts. Yeah, so it has some sodium. So sodium is Na. It has some potassium. Potassium is K. It has some chloride. Chloride is Cl. So you know that it's got these other elements, and it's all dissolved in what? Water. Okay, and they have, yeah, unless you get the 0, it's got sugar in it too. Okay, so those are really the components, and then they add flavoring, and they add some kind of color. So you can get like the berry, or you can get the limeade, or the orange, whichever color you happen to like. Okay, so would you say that that is a pure substance or a mixture? It's a mixture because it's mostly water. So when you think of things that are dissolved in mostly water, then that's going to make it a mixture. But when you pick it up and look at it, is it uniform, or does it have stuff floating in the bottom? Should be uniform. If it's floating, I put that one back. Take the next one. So if it's a mixture, it would be homogeneous, heterogeneous. Homogeneous because it looks the same. Chocolate ice cream. So again, you have to think, all right, so what's in ice cream? Sugar, milk. Okay, so right there, sugar is like a solid, like granulated, and then milk or cream is a liquid. So what do you think happens? It all gets mixed together, so you know it's a mixture. And when you look at it, it's uniform. So you would say, well, what if you have chocolate chip ice cream? Okay, now you look at it and you're like, well, it's still a mixture, but in fact, can you see parts? Yeah. Pieces, yes. Okay, so in that, it's still a mixture. Cream, sugar, and all these things mixed in, but it's heterogeneous. So like if you get water out of the tap, in reality, it's probably a mixture. It probably has some small amounts of salts dissolved. But if you get what they call distilled water, the way that they make distilled water is they took water from the tap, they boil it till it becomes a gas, and they collect that water vapor in another container. So the only thing that goes out of the water from the tap is just pure water. So what you have in distilled water is just H2O. So that would be what? Pure substance or a mixture? It's going to be a pure substance because all of those components are one thing. And you know it's H2O, so you know that it's a compound. There was like in Nashville, was it Sunday night? That they had a boil alert? Because they detected poop in the water. It's like a coliform numbers were above acceptable levels in Nashville. I was like, huh? Yeah. Well, you'd be surprised. I mean, because it ends up being chlorinated. Yeah. So because of that, it is disinfected. And so the odds of any of that surviving, but there's a certain number that's actually considered like, it's like low. So tap water, Nashville water, it's got water. If it's city water, you've got chlorine. What else do they add to city water? Fluoride. Okay, so it is a mixture. Okay, it's mostly water, but it does have things that are dissolved in or mixed in. And in theory, you really shouldn't be able to see any parts or pieces. So it should look homogeneous. But that's actually different than distilled water. In lab, we'll use distilled water when we do chemical reactions because we don't want those other compounds being added to a reaction because it may end up affecting it. So I got a couple other ones. So if you see a substance and it gives you symbols, so there's a number of symbols that you'll need to learn, like for this class. You don't have to learn all of them. There's 118. That's a little old as far as a chart. You don't have to learn all of them. We're really going to stick with the big ones. Okay, but sodium is actually one of them. So Na is sodium, Cl is chlorine. When you see them together, that's sodium chloride. So this is table salt. So when you look at crystalline table salt, if it is just pure non-iodized table salt, then it's NaCl. So is that a pure substance or a mixture? It's a pure substance. Is it an element or a compound? It's a compound because it's made of two or more elements. So pure substances are either elements or compounds. Mixtures get defined as homogeneous or heterogeneous. So 14 karat gold. Anybody know what that means? You've probably seen, like, because they're 14 karat, there's 10 karat, 14 karat, there's 24 karat. 24 karat is actually pure gold. What's the problem with making jewelry out of 24 karat gold? It's very expensive and super soft. Like, you can bend it. So, you'd be like, oh, I got these earrings. And they're gone. So what they did is they added other elements like zinc to it. Okay, and so what that does is it just makes it hard. So they take the gold and take zinc and they heat it up and mix it. And when it cools, you have a nice solid gold earring instead of something that's all bendy. So if it's 10 karat, then that means it's not pure. But you would need to have that information. That's why I said I would always give you that information. But when you look at it, does it look uniform? Okay, so it is a mixture and it is homogeneous. So based on what we've been talking about, a cup of salt water is a mixture. And if it's just a teaspoon of salt and water, it would be homogeneous. You could put a teaspoon in, stir it up. It would completely dissolve. You wouldn't have any solids left behind. Oxygen gas. Like if somebody has to have supplemental oxygen. Pure substance. Why? Because oxygen's on the periodic table. If it's oxygen gas, it's a pure substance and it is a element. Even though you see it written as what? Yeah, it's always written as O2. You don't just write O. Okay, so it exists as two oxygen atoms as one unit, but they're both exactly the same. So that would still be considered elemental oxygen. That would still be a pure substance. Paint. So paint is one. You need some information. You know it's a mixture. What would you say?
Latex or oil paint.
Okay. Okay, so some have actual visible flecks or paint colors like metallic shine to it. So that you would say that it's heterogeneous. But to some degree, it also depends on if you've stirred it. Right? So if you go to Lowe's and you get your paint and they shake it on the little shaker and you go straight home and use it, it's beautiful. You don't have to do much stirring. But if you ever had to like do touch-up paint and you're like, get the paint that's in the closet like from 5 years ago and you pry it off and there's rust all around the top. But when you look at it, what do you see?
It's separated.
Yeah, it separates. So there's like this liquidy kind of stuff. If it's oil, that's an oil-based type of liquid that you have to mix it back down in. So latex is water-based. So it really depends. It's still a mix. Oh, sorry, not that one. It's still a mixture, but whether it's heterogeneous or homogeneous, that's going to be a factor of whether or not it's been stirred. Not been stirred, it's going to have layers. It's going to separate out over time. Ammonia. So sometimes when you see something, you're like, well, I'm not really sure what that is. Like I've heard it before, like I've heard it in like maybe a cleaner, like some people clean with ammonia. That like would take my breath away. But ammonia is NH3. So it would be a pure substance. And it would be a compound because you see N, which is nitrogen, and 3 hydrogens per particle. The air in this room, 79% nitrogen, 21% oxygen, smaller amounts of the others. Can you see layers? Can sometimes when it's foggy, okay? So there are periods of time that may happen, but typically, no, homogeneous. Asphalt, mixture. Homo or hetero? Why? What do you see?
Depending on the asphalt, there's gravel.
You can see gravel. You can see like little rocks. You can like the tar. Very good. Okay, so I'm going to quit, and I'll usually start right at 5:30, and then we'll go till 6:45 because that gives you your 15-minute break. I'm supposed to give you a 10-minute break every hour, but we'll just do the hour and 15 minutes, and then that way you have a break. So then on Wednesday, if you're in my night Wednesday lab, then that'll also give you a little bit of time in between having to go upstairs. Okay, so sort of how we'll run them. I will have this posted. You could go ahead and start looking at the classification of matter. There is a dynamic study module in MyLabs Plus that is covering this, talking about pure substances and mixtures. So since we've just finished it, feel free to start working on that, and also try to get chapter 1, the pre-lecture. You have a 2-week free trial, so even if you haven't gotten your book, you can still log on to MyLabs Plus through Moodle. I've got a couple of links scattered throughout the Moodle page, so you can go ahead and do those.
Do you want our name tags?
You know, keep them, if you keep them and then just put them out for like a couple of weeks, because that'll help me.